Hello everyone, welcome to this week's video. Today we're going to be talking about the orbiter EPS, or electrical power system. So of course the orbiter needs to be in contact with the probes, bring the probes to Mars, and relay that data to the Deep Space Network or to the Mars network. And so you want to verify that A, it can generate enough power and be able to store that power. Of course, storing power is really only needed during the eclipse section of the orbit, and power generation is just really nice to have because if you're excess, then you don't have to really worry too much about degradation or something being overloading. So with that being said, so this is the Python script. It's one of the shorter ones I actually have. It's 200 lines. So we'll go through our inputs here as standard. So our array is 900 watts, and we kind of say a dust factor. Dust here is degradation. I just don't feel like changing it at this point. And we'll just assume that it degrades at 85%. And then we're also going to say a non-optimal angle here. And our efficiency is low, 29%. I expect the orbiter to use more of a 95%. So this is very conservative in terms of power generation. Solar constant at Mars is far lower than that of Earth. It's just a simple truth. And we want to calculate the array in watts. So we do the effective, and it is equal to the rated times ETA. So the bus. So we use a 28 volt system on the orbiter and on the probes themselves, and we use a nickel metal hydride battery. Yeah, you don't really hear that too much about any new projects, admittedly, but I personally have a love for nickel metal hydride. They have significant flight history. They're wicked robust and durable, and they perform rather optimally at various temperatures, and low temperatures and high temperatures. Primarily those low temperatures is what we care about in spacecraft. And so that's super important. So we have a 950 watt-hour battery. Technically it's actually made up of two batteries, and they're both relatively small. Energy density of nickel metal hydride is a little bit higher than it used to be. And they're made up of F-cell batteries, actually, in containers. And it was just deemed that was the best way to design the system. Round-trip efficiency. So what is our, maximum power point tracking efficiency? That's like our power architecture for solar charging. I assume 77%. It'll be higher than that, I hope, but again, we're going on the conservative side. State of charges. So we start at 80%. Why not 100? Well, it's kind of more important to be able to see that it'll actually be able to charge. Minimum before we start shedding loads. Shedding loads is a power system term effectively for just like you're dropping a bus. So you're dropping any unnecessary loads. And on the orbiter, there's a lot of unnecessary loads. It's got science, and it's got communications, and it won't be expected to be transmitting constantly. It'll be in the X-band for most of the time, and so the transmission data is pretty short. So, with that being said, here are our loads. So we have sun. So this is kind of our maximum power that we would expect in the sun, and it's 555 watts. Pretty low compared to our panels. It's about a third of the panels, and during the eclipse is 275. Again, these are conservative on the high side this time. And then for the simulator, you can do multiple orbits. I'm doing 40, just feels right. And then basically this is just determining you know, our start times and then the actual power. It's very simple math. So let's run it. Let's see what happens. Boom. So here's our first figure. Actually, I'll not move it. So this is our sunlit versus eclipse power profile on our first orbit. That is the important part. So as you can see, we are generating power for the first part of this orbit, almost to 90 minutes in. Then we hit the eclipse, and then boom, we're back. And so we can see that our load is here and our generation is here. Okay, well look at this. Our state of charge, well, that looks pretty consistent to me. It starts at that 80%, just like we said, and it hits 100. Then goes down, goes up, goes down, goes up. That's exactly what we want. We don't see any loss. So totally fine sizing. Sure, we could size up the battery. I could probably put in 2 more sets of those batteries and get 1,800 watt hours of battery. And that would effectively mean that we wouldn't need as large of a solar system. But I think we're being very conservative on all the values anyways, so it doesn't really matter that much. Okay, so let's look at the printouts. So, power at Mars, we design it at 400 watts. That's how much we want to generate at Mars. Our solar irradiance, power efficiency, and so this actually kind of does the reverse of what we would expect, and so we need at least 5.27 meters squared of solar arrays area instead of doing the opposite. And this way kind of helps because you know you can't just say the array is the entire size of the panel, because that's just not true. A lot of space-rated panels are only 70 to maybe 80% of the actual area is the efficiency. Effective sunlit power is 650 watts. In our actual system, it will track, but we automatically always handicap ourselves with 80% or 85%. Sorry. Our orbital period is 210 minutes, and our sunlit is 1 hour and 40, and eclipse is 0.70. So here we've just got a printout of per orbit energy balance. As you can see, our net is about positive 225 watt hours, which is plenty. So we are fine. No need to upsize anything. So that is the basic design of the script of the orbital EPS. And some updates on the paper is it's going well, and I should have a rough draft on the GitHub pretty soon. Speaking of the GitHub, this entire script is on the GitHub. So thank you very much for watching. Have a wonderful day. Bye-bye.